Okay, welcome back. This is the fourth video in the series on electronic structure, and where we finished in the last video was we specifically looked at electron configurations moving down groups, and what we were interested in that drill was to look specifically at what the outer shell of the various elements in a particular group, what that looks like, and I demonstrated how once you have the electron configuration that you can identify the outermost electrons on the surface of a given atom as long as you know the group and period number. And then I raised the issue that you could break the periodic table down into blocks. And so that's where we're going to start with this video. There's two goals of this video. To point out that you can break the periodic table into blocks, which helps you rapidly develop the electron configuration for any atom, number one. Number two, what I want to do is take you through a few examples where we do the electron configuration for an atom that requires the use of the d orbital, so you can see how those fill. And then in the last part, what we're going to do is we're going to pick a number of elements out of this portion of the table, and I'm going to show you how to define the outermost shell without actually having to write the whole configuration out. Alright, so the first thing before we move on, over on the left side of the table we call this the S block. Alright, keep in mind that the first period, that's going to be hydrogen and then helium, moving left to right. These two elements only involve energy level 1 or an s orbital, simply because they have 1 and 2 electrons respectively. Elements that fall under hydrogen and underneath helium will appear in one of 7 periods. And remember that the period number is a reference to the energy level that's being filled as you move left to right across the periodic table. So for example, when we start with lithium, which is the beginning of period 2, we know that we're filling energy level 2 as we move from lithium to neon, which is in group 8A. Now, the S block, what we call the S block, is always going to be group 1A and group 2A. So we know as we go from lithium to beryllium, we're filling the S shell of energy level 2. By the same token, if we move down 1, we're filling the S shell of energy level 3. On the right side of the periodic table, in the nonmetal section, essentially, well, it includes some other elements too. Nevertheless, we call this the P block because once we filled the s orbital here in 2a, the next option as we move to the right will be a p orbital, except once we've gotten down into the energy levels far enough to where we start at period 4. Here's where we enter into the d's. So if you spend some time looking at this, you can see that whenever you're in a certain region of the periodic table, you should be able to know automatically which orbital system you're filling. If you're over here, you're always going to be filling a p system. If we're in the middle of the transition metals, you're going to be filling a d system. And if we're over here in group 1a or group 2a, we're going to either be filling we're either going to be putting 1 electron in or 2 electrons in, depending on which element we're dealing with. Alright, so what we're going to do now is practice this a little bit. We're going to start with calcium, and I'm already presenting you with the electron configuration for that particular element. And we're going to move 1 element to the right. The next element is scandium with 21 electrons. And what we're going to do is we're going to take scandium, which is the beginning of the D block. We're going to take manganese, which is in the middle of the D block, and then we're going to take zinc, which is at the end of the D block. And these 3 elements are all period 4 elements. So in other words, we're filling energy level 4 as we move left to right across the table. Now, so let's go ahead and start. So for scandium, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. So we've added 1 electron into the d orbital in order to write the electron configuration for scandium. Now, we're going to move to manganese, which is several elements to the right of scandium, and we'll go ahead and do its configuration. So we have 25 electrons to do. So I'm just going to begin. We have 1s2, 2s2, 2p6, 3s2, 3p6. Now, we've got 18 electrons to this point. I go to the 4s and I add 2 more. Now we have 20. We have 5 left to go. So they're going to go into the 3d, so it'll be 3d5. And that's 25 electrons. All right, now for zinc, which is 30. So we start. We have 1s2, 2s2, 2p6, 3s2, 3p6. Remember, we're 18 electrons out to this point. 4s2, now we have 20, and we have 10 to go. So they're all going to go into the D system, 3d10. So zinc finishes the D suborbital. And once we move to the next element to the right, we're going to be in the P series, which is in the P blocks. Okay. Now, what I want to do next is address the fact that in order to find the outer shell of a particular element, you don't actually have to write out the whole configuration. In fact, that would be the safest bet. If you're not able to understand anything else, the safest bet is to run the whole configuration. But there's an easier way. So what we're going to do is we're going to write the outer electron configuration for arsenic. And the first thing I do is make the observation that in the periodic table, arsenic appears in group 5A, in the same group where we have nitrogen and phosphorus, and arsenic is actually 3 elements down. To make things clear for us, what I've done with these red numbers is put in the period number. So arsenic is in energy level 4, and it's in group 5A. The 5 tells us that there has to be 5 valence electrons. So how, by utilizing this information, can we literally just write the outer configuration? The easiest thing to do is to look at the element that's at the top of the group and recognize that its outer shell is this right here, 2s2, 2p3. So when we move down to arsenic, arsenic is in energy level 4. Its outer shell is going to mirror this. The difference is going to be that we need to change the numbers. So the outer shell of arsenic is 4s2, 4p3, and we're done. And we didn't have to write out the entire configuration to figure that out. We just had to utilize the definition of the group number, which gives us the number of valence electrons, and then we had to know our period number, which tells us which energy level this is in. Okay, let's look at another example. What if I want to know the outer shell of gallium? Same kind of drill. I look to see what group it's in, and I see that it falls in group 3A, which means that it has 3 valence electrons. Then if I scan down to find which energy level it's in, I see that gallium's also in energy level 4, like our last example. So what I do to figure out the outer shell is I go back to the top element in the group, and I identify what its outer shell looks like. And for boron, it's 2s2, 2p1. So I know automatically what the outer shell of gallium is going to be. It will be this configuration right here, except that we need to change the numbers to indicate the correct energy level. So gallium is going to be 4s2, 4p1. This is its outer shell, and I didn't have to run the whole configuration to figure that out.